All right, so we're going to do Chapter 7, Practice C, Problem 4. So we're going to write our given, and we're going to write our find. We're going to chunk. So it says two satellites of equal mass. If their masses are equal, that means that M1 is equal to M2. And that's important. I'm going to write that down. They're put into orbit 30 meters apart, so the distance between them is 30 meters. The gravitational force between them, F subscript big G, is 2.0 times 10 to the negative 7 newtons. A, what is the mass of each satellite? And B, what is the initial acceleration given to each mass by this force? All right, where do I start? Well, first of all, I'm going to start with my equation. So I know F of G is equal to big G, the universal Newtonian gravitational constant, M1, M2 over R squared. But what I want to do is solve for M, but I know they're equal. So instead of calling them M1 and M2, I'm just going to call them M. So if I call them just plain old M, because they're equal, M times M is equal to M squared, not 2M. So at this point now I'm going to rearrange my equation to solve for the unknown in terms of the known. So I'll multiply both sides by R. So F of G R squared is equal to GM squared. I'll divide by big G. So F of G R squared over big G is equal to M squared. And then I'm going to take the square root of both sides. So I'm just doing my intermediate algebra steps so I don't make a mistake. And then again, what I'm going to do is I'm going to check my work before I get my final answer. So now I'm going to substitute in my values. So I have 2.0 times 10 to the negative 7 newtons times 30 meters squared divided by 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Now remember, in physics, we have a foolproof way to always check our work by looking at our units, and if we can't carry our units and cancel them, we can check our work. So in my numerator here, when I square the 30, I also am going to square the meter. So this is a meter squared. So this meter squared can actually cancel with that meter squared. This Newton can cancel with this Newton. So underneath my radical, I have 1 over a kilogram squared, which is basically under the radical a kilogram squared. Because don't forget, 1 divided by 1 over a kilogram squared is 1 times a kilogram squared over 1. But most of us don't need to write that out. So when I take the square root of the number, I take the square root of the unit, so I end up with kilograms, which is the correct unit for mass. So I know I did it correctly. So that comes out to be 1.6 times 10 to the 3 kilograms. So carrying my units through and canceling them helps me check my work. So that's part A. So now part B asks me what's the acceleration. Well, I know Newton's second law says F is equal to ma. So A is equal to F over m. So my force, 2.0 times 10 to the negative 7 newtons, divided by the mass that I just found, kilograms. Now if I want to check my units, a newton is a kilogram meter per second squared. So this kilogram cancels with that, and I end up with meters per second squared, which is the correct unit for acceleration. So when I put the numbers in my calculator, I get 1.25 times 10 to the negative 7 meters per second squared, and then in correct significant figures, 2 would be 1.3 times 10 to the negative 10 meters per second squared. So the little trick to this one was saying the masses were equal, that the masses were equal and that m times m is m squared, because this way I was rearranging the equation to solve for that. So that's why this one was a little bit different than just substituting in the values and finding the gravitational force.